All right. So, Andrew, we're getting ready for live design here this morning. Welcome
Yeah.
everybody to the chat who might be joining us. We're going to get started here shortly. Andrew is going to be talking about bikes today. So, Andrew, I'm not big into bikes. Tell me a little bit. What's changed in the last 10 years with mountain bikes? Is it materials? Is it the structure, the geometry on them? Like what's been some of the big changes?
Man, I mean, it's honestly, it's all of the above. And in the last 10 years, yeah, it's done a lot of stuff, right? I mean, everything, even down to how the wheels connect to the bike, are things that are kind of new within the last 10 years, that kind of technology. Do you remember those old things that you would put on a 10 speed? It had a little ratchet and a spring, and it would kind of connect the front wheel by you spin the thing and then ratchet it down to connect the front wheel to the bike, and it would
Yeah, of
take the front wheel
course. I
off.
used to
Yeah.
when I used to ride a bike, that's how I'd have to fit it in my hatchback. I'd have to take that front
Yeah.
tire off.
Yeah. Pop that up. It's called quick release, right? So those
Yeah.
were around forever. And in the last 10 years, they've changed this thing called through axle, which is kind of the same principle, but instead of this really skinny wire, it's a thick, hollow steel shaft. And the reason for that is because braking has gotten to be so strong on mountain bikes and road bikes in the last 10 years, they found that those quick release would start to flex under the really crazy braking force.
Wow.
And it would kind of like maybe a car analogy. I know you're a car guy.
Like a
Like
like a
how
torque steer, like they call that a torque steer.
that's exactly what I was gonna reference. Yeah, like torque steer in a car, it's kind of like the same but opposite, right? So hitting the brake so hard, it's forcing your front wheel to actually turn, or your rear wheel to get out of line from your driving, or from your path. So those through axles actually were a crazy upgrade in the last 10 years. In fact, that's trickled down to road bikes and gravel bikes, and now that's pretty much the standard. So that was a big one, even though it's kind of subtle. You may not even notice it on a bike.
Yeah, it's been a long time since I looked. Really quick, want to welcome, I see Brian Zeiss in the chat. MC, good morning to you too. Mikhail, Eldrick, Adag, good late evening to you as well, everybody. We're going to get started here in just a minute or two. Me and Andrew are just chit-chatting, getting ready to show you guys some really cool stuff today. So what else are some of the big changes? I know you said materials were a big change, but that's
Yeah.
not like new. You were talking about the saddle, which forgive me, I thought it was called the seat. You said they're 3D printing them now?
Yeah, and it's not just like these really esoteric companies 3D printing saddles. I mean, it's like Specialized is printing saddles. So one of the biggest bike manufacturers on the planet is now 3D printing saddles that, I mean, they can just achieve so much more, like, when it comes to comfort and being light and being strong. So yeah, 3D printing saddles, like, for the consumer market. Yeah, not just like some dude on
Okay.
on like Etsy saying, "Hey, I sell saddles that I 3D print." Like,
This
yeah,
isn't like they've got a maker bot and they're cranking saddles out. They're
right.
doing, I'm assuming, like a printed nylon embedded or carbon fiber saddle, kind of like the Mark Forge technology.
That I think the Specialized saddle that I saw, it was a really stiff rubber material.
Okay.
So yeah, and who knows what type of machine they're using for that? I mean, it could be like Objet, or who knows, something that prints rubber. But yeah, I mean, on the inside, it's just all hexagons everywhere. It's all honeycombs. Super cool.
Hey, Kolbish Fusu, I hope I got that right. In India, welcome. Sarbjet Singh, welcome. Mohammed Fiaz, welcome. Planet Software, welcome. Justin Burton, great to see you here as well. What do you want to do? You want to give it another minute here, Andrew? Give
Sure, we
people
can
some
give,
time
give
to
another
jump
minute.
on?
Yeah,
So,
yeah.
so mountain biking's new for you, but you
Yes.
rode bike. You used to ride a road bike, I think you said?
I still ride a road bike, but I've been a road biker, gravel rider for about 15 years. And just 6 months ago, I got my first mountain bike. I mean, I knew it was going to happen at some point, but because it's just, the older you get, the more sketchy it is to ride on the road. I mean, like, semis passing at, like, 6 inches from your left side when you're on the shoulder. After a while, yeah, you think about your kids and your wife and your family every time. You're like, yeah, maybe I should ride on the dirt, because mountain biking is actually far safer. I'd rather
Okay.
break a bone than get plowed by a semi truck. So I still ride both, but yeah, mountain bike is kind of a new thing for me. Yeah.
All right. Got a couple more people joining us in the chat here. CAD Cam 100 Exercises, welcome. Mike Sandy, welcome. We know you're in the background there. Puebla Mex, Solidworks User Group, welcome to the Solidworks User Group as well. What do you think? You want to dive in here and get going,
Sure.
Andrew?
Yeah, let's jump in.
All right, I'll do the official intro and start, and we'll get things kicked off. How's that sound? So I want to welcome everybody this morning, today, this evening, wherever you're joining us from, to Live Design on our YouTube channel. This is a bi-weekly broadcast we do where we're going to show you how to do really cool things and solve problems in the SolidWorks portfolio of tools that's available to you. I'm joined today by our presenter, Andrew Gross. Andrew, welcome.
Hey, thanks, Jeremy. Happy to be here. Thanks, man.
Yeah, we're going to bring you on a little bit of a journey. Andrew, you're going to be showing us how to simulate a 3D model in SolidWorks to kind of mimic the characteristics of the real world. That's the idea,
Yeah,
right?
that's right. Yeah.
All right. So, and you happen to be a mountain bike enthusiast. So what are we going to be looking at today specifically?
So we're going to be looking at, so I have a 3D model of my mountain bike that I put together. That was kind of a fun thing to put together. And what we're going to look at today is, this is called a full suspension mountain bike, right? So you have your front forks that are like, have a spring and damper system like a suspension, but also the entire rear section, the swing arm, that also has a suspension system as well. So what we're going to look at today is we're going to kind of talk about how we can tune a suspension system for a ride based on how fast you're going, how big the bumps are, rider weight, all of these different things. And the coolest thing about mountain bikes, and especially their suspension, is that you can really, really tune them. They're air springs, right? So you take a little pump and you can pump up the front and rear suspension, so you can change that spring rate based on the PSI of the suspension, which is pretty slick. So you can really kind of tune the bike based on the ride. And that's what we're going to do today. We're going to assume a certain number of things, or certain things, and then we're going to look at and simulate kind of a mountain bike going down that terrain, and then we can tune from there.
So Andrew, these springs and dampers,
yes.
based on where you're going to ride for the day, you would make that adjustment. Is that how that would work? So the folks at home who might not be into mountain biking like myself, so I can decide where I'm going to go today, and I can make those adjustments ahead of time.
Yeah, you absolutely can. You bring this little pump. So basically, like if you're doing like really fast downhill with not a lot of bumps, right? You might want your suspension be a little stiffer. But if you're doing like, single track, meaning like small stuff with like big rocks and stumps and things where you really, really need a lot of travel on both the front fork and the rear suspension, you would reduce the PSI of your suspension system. So your spring rate, you in effect reduce that spring rate. It works like a progressive spring, and you can get more use out of the suspension. And the real goal of a suspension is not to like make it more comfortable necessarily for you riding, although it does make it more comfortable. The purpose is to keep the rubber on the path as long as possible, just like in cars, right? It's like if you have like an underdamped suspension, right, and your kind of wheels are bouncing all over the place, that means that you have less rubber on the road, which means less grip and, also less comfortable ride. So if you can tune the suspension to really match the ride, the speed you're going and the bumps. So yeah, that's the purpose of it. It's pretty cool.
Okay, so how are we going to simulate this in SolidWorks? In the real world, feel is everything. How do we simulate feel or this terrain inside of SolidWorks?
All right, so we're just going to start with just a simple model, right? But if you guys watched the SolidWorks live design, Jeremy, maybe it was like a month and a half ago. If you remember, Mike Sandy had a whole episode on simplifying a model for simulation, right? So that is the absolute rule of anytime you simulate anything: simplify, simplify, simplify. So you can start with a model that has a lot of detail like this, but one of the first things we want to do, right, we want to simplify it. You know, you can get entire groups of parts here that we have, and I could just kind of like blow these guys away. I can, you know, say suppress them. Now, I'm not going to go through this entire process of simplifying everything because there's a lot of stuff here. So we're kind of
so if you want to see where Mike Sandy showed how to do that, we have a playlist on our YouTube channel where we have all of this year's live designs, and there's another playlist with all of last year's. So go check out Mike Sandy to see how to simplify your models, right, Andrew?
Yeah, absolutely. He'll show you some really, really awesome techniques that I won't have time today to talk about, but great ways to simplify your model right on the fly, do it fast, and using a lot of like selection and suppressing tools that we have built into SolidWorks. Pretty cool stuff.
All right. So you're gonna open up a different file here?
Yeah, we're gonna do kind of the Martha Stewart like oven, like, you know, here's the cake unbaked, and I'm gonna pull out a baked cake.
All right. So why don't, while you're doing that, I'm gonna ask the audience a question. How many of you folks mountain bike in the audience? Give us a one in the chat if you mountain bike, or maybe we can have our new back-end producer try to do a poll out there. Do you mountain bike? So we'll see what happens there. Either do a one, or you'll see a poll show up here in a little bit.
Cool. I can't wait to see how many people mountain bike, or even if you bike. What about if you put a 3 in the chat if you just ride a bike?
Yeah, how about that? I mountain bike, ride a bike, or I don't ride a bike.
Don't ride a bike. Something like that. So this is my simplified model. You notice that there's no place I put my hands. There's no handlebars or brakes. There's no saddle. This could be somewhat uncomfortable. You wouldn't ride a bike like this. There's no crank. There's no chain. There's no derailleurs. So when you think about the suspension of a bike, those things don't really contribute to the behavior of a bike and the suspension of how the bike moves. So we can replicate that by adding weight to the bike, right? Because we're taking weight off. But as far as the function, they don't really do much. So I'm going to start today by just kind of, I've mated this together partially, but I wanted to spend some time and put some additional mates to this to kind of show some kind of cool ways that we can simulate just in SolidWorks, using SolidWorks assemblies, how kind of this thing moves around. So you'll notice that, you know, the front end is not connected. It's kind of connected in the rear here, but it's all over the place. So let's start by just connecting the front end to the forks. So easy stuff, right? Couple cylindrical faces. I always use quick mates. I think they are, like, when these are introduced, since they're introduced, I rarely go to the command manager to click the little paper clip. Never do that anymore. So, right, a couple concentric mates here. I can get this done really, really fast. So now that we have this mated, right, we can move it up and down. You can see that we want to set some limits, right? So my bike.
Yeah, you don't want the forks coming right off. Right?
No, the forks coming off when I'm riding, right? Because I'm just usually doing wheelies all the way down. And I don't want my front wheel to pop off, right, when I'm doing those wheelies. So I want to put some limits here. And what I'm going to choose a limit mate. So I know from my bike, I know based on this gap from this flange to this flange, I know the limits of my bike of what the suspension can do. So by selecting this face, see if I can get it. Take a couple tries. Come on. There we go. Got it. So this face to, sorry, make you dizzy here with all my spinning. To this face, I know the distances here. So I can create what's called just a simple limit distance mate. And this does exactly what it says. It's pretty simple. It's like, well, what's the maximum distance? Well, I know that, and I have a little piece of paper here because I always forget the numbers. So I know the maximum this is 7.25 inches max. And the minimum distance here is 1.5 inches. So I have about close to 6 inches of travel, not quite 6 inches of travel.
And then that first number that you see there, that was the current value that's in there. So folks at home know if you want to make an adjustment and like set it to like an absolute value, you could enter that there as well.
Yep, totally. Thanks, Jeremy.
So Andrew, really quick, we've got the results for our poll in already. So you've got a lot of viewers interested in this. 56% of the audience mountain bikes. So
no way.
Got a captive audience.
Wow, that's awesome. Hopefully see you guys out on the trail.
And Andy Rammer says he mountain bikes frequently, but he really wants to start mountain biking.
Yeah. Well, Andy, you should start mountain biking more because it is like the funnest thing ever. It reminds me of being 12 years old and like killing it on a BMX. It's the funnest thing. It just reminds me of being a kid. So yeah, now I have my limit mate, right? So I know I have my travel set here, my max and my min travel. Cool. So now let's start working on the rear suspension. Kind of move that down a little bit. Okay. So my rear suspension, well, it's kind of all over the place, right? So we're going to connect our suspension together here. All right. So the easiest way to do this, I think, is using another pretty cool kind of SolidWorks technique. Again, another thing I love, this component preview window. All right, what the heck is that? If you've never seen that, I urge you to click it because it's the coolest thing. So now I have the cylinder, which is the top half of my suspension. I can rotate and pan it and zoom in and click these faces completely independent of the left side. But you notice that when I click a face on this in my little preview window, that same face is clicked on the left side as well, right?
So to be clear, you're not actually opening the component in its own part window. You're actually bringing up a preview window where you can manipulate that part in the context of this assembly.
Yes, it's awesome. So it just makes making some of these mates really easy. So I don't have to stick on one window or the other. You notice I can just click this cylindrical face, and then create my quick mate super fast. And boom, there we go. Now, just like the front, we want to create that limit distance mate. And this is where things get even more tricky, right? Because there's a face in here that would be really, really hard for me to get, but I can grab it in here. So if I open my suspension up just a little bit, I can just kind of use select other here. So if I use select other here, oh boy.
Oh, you did normal too.
That was a fat finger. Okay, so if I choose select other here, I can find this face, but I can also control click this face. And now I can choose my limit distance mate. So I'll choose mate. I want this to be, oops, I misclicked again. Jeez, what's going on here?
Oh, that's all right, man. We do it all the time. We're human beings, Andrew.
All right, let me just make sure I get the right face. My air can, yeah. And then this face, and I should have my limit distance mate right there. Got it. Okay, so let me go to my little cheat sheet.
I was wondering what you were doing because a minute ago you said you don't even like to bring up the paperclip menu.
I know.
I was like, well, he's going to it now, so there you go.
All right. So now when I exit this preview, we can see that I have my rear shock now set up a little bit. It's not really moving too much because everything is so wonky. So this is another cool thing that I really like to use. If you right click a part or a subassembly, you can choose to temporarily fix it. Remember this one, Jeremy? When did this was released? Maybe 2015 or something like that?
Yeah, no, this was a really cool capability, especially when you have a lot of movable components in your design. This gives you the ability to lock things down so you can focus on mating those components together.
Totally. So I can, because my frame is still kind of wonky, still moving around, and that's on purpose. I want to give the frame a certain amount of movement, right? Because we're gonna be able to use that. But now that I can fix it, so now I can kind of inspect this and make sure it's working properly. So that's working properly, and my front end's working properly now too.
So Christian N has a question. He asks if this is in SolidWorks 2021, and yes, we're doing everything you see today in 2021. But a lot of the capabilities Andrew is showing have been in the software for a while. That fixed components, for example, that's been in there a couple of years. I know component preview, I think that was 2019, maybe we added that.
That sounds right. 2019, 2018, that time frame for sure. I trust you more than I trust me.
Oh, I know at 3D Experience World, I happened to do that tech preview for component preview.
That was a good one. All right, so again, if I start moving things around, everything's just going bonkers here, right? So we need to give it just a little bit more structure before we start kind of building our test rig. So the next part is building our test rig. So imagine you're like bombing a hill on a bike, right? And you're going over bumps, front wheel, back wheel, bump, 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 bump. You're going to be rotating. Like if you look at the global view, you're rotating really around the CG, right? The CG of the bike, and the rider, right? So if I were riding this bike, if you can see my mouse, the CG is probably going to be around here, right? So if I really want to take the time, I could build some dummy geometry, and I could use that piece of dummy geometry as kind of like a rotation point. I'm going to kind of cheat and just use some geometry that's already here on the frame as the rotation point. But what I'm doing really here now is I'm assuming a center of gravity that we're going to rotate around, and it's going to make the simulation way more realistic.
So before you do that, one thing I wanted to note, all your components were moving around. There's no fully defined components in the assembly. So, but this is specifically because we're doing a simulation of this real world environment, and you need that motion. In the design phase, you would probably have that frame locked down and everything mated to it, correct?
Totally. Yeah, exactly. That's how I would do it. And that's how my full assembly, the frame is the front triangle of the frame is fully fixed. And then everything is based around that. That's exactly how I built that.
Okay.
Yeah.
I just want the people in the audience to know, like, we don't like for normal day-to-day design, I wouldn't have all your components floating in space. You always want to have a component fully defined and then build from there.
Yep. And so in this assembly, it's a good point. Nothing's fully defined, and it won't be. And that helps to make it a little more realistic. So I'm going to choose this cylindrical cutout. This is going to be what I'm going to assume is the CG, just because it's easy and it's there. In real life, right, I'd want to calculate a more precise one. So I'm going to mate that to the right plane. And you're like, wait, hold on. How do you mate a cylindrical face to a plane, right? So I want to get quick mates again. So I have to kind of click these just one more time. So I'll click this face. Plane. And now I have my quick mates. So what comes up is tangent. It's like, okay, well, I can do tangent, but I can also choose a distance mate. So a distance mate with a cylindrical hole and a plane. What? How does that work? Well, what it does is when you select that hole, it's really selecting the axis of that hole, right? That kind of those temporary axes, right? It's connecting, and what it's mating is the axis of that hole to a plane. So now if I move my bike around, you'll see it's kind of limited up in it's limited now to just being able to rotate around that fixed point, but it can't move, in this case, negative or minus in the X direction. And that's going to help me. So that means my bike can rotate and move up and down, but it can't go like this. And that's exactly the movement I want, right?
So
when I simulate.
That's a cool trick. I mean, otherwise, what, you'd throw an axis in there or have to turn on temporary axes or something like that. You can just mate right to that cylinder. That's cool.
Right to that cylinder. Yeah, it's pretty cool. It's pretty cool. All right, so I'm going to fix this one more time, temporarily fix my frame. Just because I want to extend I want to kind of level this out. Great. So that looks good. All right. So now that I have my bike all done, now we're going to build a testing rig. And this part I think is pretty fun. So I have a little bit of geometry here. I'm just going to unhide. And you'll see it's really just simply, it's a kind of like a drum with some bumps on it, some 2-inch bumps, and an axle. And that's it. And it has some movement. So I can move this up and down, and I can rotate the drum around the axle, right? So 2 degrees of freedom here. So the first thing I want to do is so that's great. That's great for the front wheel. But now I want to create the same sort of rig for the rear wheel. And we're going to use something that a tool that I absolutely love called Copy with Mates. So this is one of my favorite tools. So if I select this axle, if I right click it, I have this option, Copy with Mates. So what does that mean? So I know I want to make a copy of it. But what Copy with Mates does, it takes the mates that are currently associated to that part, and it gives me the option to either keep the same mate references or choose new ones from scratch, and I can go through all of the mates that are there for it. Okay, so I chose my part. Okay, next. So these are all the mates associated with this axle. So you can see on the back of the axle, I've extruded this little kind of cube piece, and that's for a reason. It's because I want to use that as some flat surfaces for mating. So I have a parallel axis or parallel mate to the top plane. Well, my new version, I want to repeat that. I want my new one to also have a parallel mate to the top plane. So I'm just going to choose the repeat button. And it's going to give me just at some strange angle, here is a shadowed preview of my new copy. Okay, so next is it's just going to go right down the line. So it's a distance mate. So my previous mate, I had a distance mate to the right plane. Sorry, I can move it around a bit. From this face to the plane. So I want there to still be that distance mate, but I want it to be on the other side of the plane. So it's pretty easy. I can just pretty quickly, I can click flip dimension. And now if I repeat it, you'll see that now my axle's on the other side of that plane. And I can even change the value. I can push it in. That's a little too far. I want it to be as close to right underneath the center of the wheel as possible. So if that was 33 inches, let's say 13 inches. And that's close. Maybe we'll get a little closer. How about 10 inches? That's a little too much. Trial and error. Now, again, if I were really to try to simulate this to get really good data, I would make sure that it is right underneath the wheel. So this is kind of a little loose here with some of our dimensions.
A little loose. So that's a question we've got in chat there, Andrew. Joshua Brown asks if this is based on ISO 4210 testing. I'm guessing we're
Nice.
not getting that precise. What we're doing is just kind of showing how to simulate it in a real world environment.
That's right. That's right. All right, so this next distance mate, I want to flip it. Okay, because I want to repeat this one, but I also want this to be, whoops, that needs to be flipped. Which one am I missing here? Well, we're just going to go ahead and skip that mate anyway. Okay, so we're going to skip this one.
So that's something to point out. You can actually pick and choose which of those mates you want to copy. You can actually shut them off and only copy some of them if you want to.
Yeah, that's right. That's right. So I repeat that one, but boy, that looks really off. So I'm going to go ahead and choose that distance, and that looks a little better. But now there we go. That looks good. All right. Just kind of got a little mate combobulated. All right, we're going to skip the last two because we're going to add those mates when we actually use copy with mates for the other part, the drum. Cool. So we're going to copy this one with mates now. All right, copy with mates. That's perfect. So this concentric, well, I don't want the new drum to be concentric to the old axle. I want it to be concentric to the new axle. So one click, boom, got it. And now this distance mate, right, which is the distance from, it's calculating the distance from the end of the axle to the face of the drum. Well, I want that to be now connected to the new drum. So I'll create that later. I can create that one later.
So I want to give a little bit of a commentary on copy with mates because it's one of my favorite features as well. We should point out copy with mates works on standard mates. So in the last few years, we've introduced some really cool mates like profile center mate. Copy with mates doesn't actually work with profile center mate, I believe. So
awesome. That's a good
keep that in mind. Like if you're trying to use it and you're like, why won't this work? So that's going to be coincident, concentric, parallel, tangent, limit, angle, all those like standard mates will work with copy with mates. But if you do like a gear or you're doing a rack and pinion or something crazy like that, you'll run into it won't copy those.
That's a great tip. Thanks, Jeremy.
Yep.
All right. So now I want to line up my two axles and my drums. So I'm going to go ahead and make that coincident. I'm going to coincident on that flat face. And now I've got a testing rig that's starting to look pretty good. So again, if I use my temporarily fix, I want to temporarily fix the axle. And I can see that, this is turning and this is turning, but they're turn. So I have kind of what I want, but it's not perfect yet. I want to be able to turn one drum and have the other drum turn as well. And for that, I'm glad you were talking about different types of mates, Jeremy, because now we're going to create something called a gear mate. And what we're going to do is associate one of these drums, how the behavior of it spinning to the other one. Super simple. Okay, so this time I actually am going to use the little mate paperclip because now I want to get into mechanical mates. And again, many of you may have never even used a lot of these. Some of these are very specific in what they do. Things like cam mate, slot mate's pretty common, hinge is common. Gear mate, I bet there are people on this call who've never even created a gear mate, or rack and pinion mate. So these are really, really cool mechanical mates that can really replicate a multitude of other, like a collection of other mates. You do it in like one shot. It's pretty awesome. So again, a gear mate. So I'll choose my two faces of my two drums, and I'll simply select gear mate. And you'll notice it's going to look at the outer diameter of those faces I selected. It sees that they are identical, right? So hit OK, and we're done. So now let's take a look at this. Again, I'm going to go ahead and temporarily fix this axle. So what happens when I turn it? Does that look right, Jeremy?
They spin together, but they're going opposite of each other. Andrew,
yeah,
don't you want them to go in the same orientation?
Oh, yeah, I do. So it's really easy to switch that, right? And so for this, I'm going to use something called breadcrumbs. So I clicked on this drum, right? And now I can look at all the mates connected to this drum, and I see my gear mate. Click that.
So that's a big tip. You can dive right into the mates of a component by simply using the breadcrumbs there.
That's right. Oops, because I was wondering.
And that is, so for Christian's question earlier, that is fairly new that the mates have been accessible from the breadcrumbs, I'm pretty sure, right? Like that's like the last few years, I think.
Last few years, yeah. So I can access that mate directly there. And now I can just simply have to reverse the direction on the gear mate. So now it should work as I expected. Yeah, there we go.
It's a little more like a pulley kind of is what you have there, right?
Yeah, a little more like a pulley. Yeah, it's like imagine if you have a chain connecting both of them, or something like that. Yeah, a pulley connecting both of them, so they're actually both rotating in the same direction. Okay, so we also know that the front wheel and the rear wheel, they're not gonna hit a bump at the exact same time, right? So we also want to phase shift our two drums because these bumps, if I haven't clarified that earlier, these bumps are replicating like a bump in the road, a bump in the trail.
Root in the trail.
A rock, exactly. Okay, so what I can do again, now I can actually, I just created this mate, but now I'm gonna disable it. Also using breadcrumbs, I click the part, I click the D key, I can now just immediately suppress that mate, right? Now I'll fix this again. So I'll go ahead and temporarily fix the axle.
You really like that fixed group. Yeah.
Because I have there's so many degrees of freedom in this model. You have to fix it or else everything just goes all over the place.
Yeah.
So I'm going to set this at about 90 degrees phase shift about 90 degrees from one another. And it probably should be 90 degrees the other way, right? So after this one hits, so this one hits first on the front and then the back. So that's about right. And now I'll just hit the D key again on my mate. And I'll unsuppress it. And now you can see it's going to kind of, I'm going to fix it again. It just makes life so much easier to fix. So now we can see kind of bump the front wheel, boom the back wheel, right? So now our test is
so instead of like dragging a piece of ground under the tires of this bike, you're basically using kind of two cams sort of to simulate those bumps happening in a specific timing with one another.
That's right. I mean, there's a million ways you can do this.
Sure.
But I felt that this was kind of the simplest way to kind of get the timing right as I rotate the drums and put the wheels on it and actually have the bike riding on this testing rig. I felt this was kind of the easiest way to kind of, set the timing. Now, again, if I wanted to be super precise, I'd want to measure the axle distance of my bike and ensure that these two bumps were at arc length would be the same distance from axle to axle on my bike. Again, this is kind of just a little demonstration. You could put that math in later. You could put it in later after you built the rig. Okay, cool. So we are getting pretty close to being ready to actually simulate this or start building a motion simulation. Okay. So any questions in the chat, Jeremy?
Not since the ISO testing one. I see we just got a question from Lolkatsnin. I hope I got that name right. Is the stream going to be on demand? So all of our live design in all of our live streams that we do every Thursday at 11 a.m. Eastern time are available on our YouTube channel. We have playlists for each of them. There is a playlist for this series, Live Design. There is a playlist for SolidWorks Live, and there is a playlist for Exploring 3D Experience Works. We're going to cover a little bit of that at the end as well.
Cool. All right, so under my SolidWorks add-ins, you can see that I have SolidWorks Motion added in. Now I want to let everybody know that SolidWorks Motion is part of SolidWorks Premium. So Motion doesn't come with.
Hold on, Andrew, really quick. You did get a question when you prompted for questions. Joshua Brown asked, he said, would a gear mate that isn't one-to-one give you like a variable bump profile? Like would that cause you over time to get like the bumps happening at different rates, simulate like different rates?
It would, but I can't think of a situation where one wheel would be getting bumps at a higher rate than the other wheel, right? Because you're rolling over it, it'd be like bump, bump. If that's the question that was asked. Yeah, interesting. It's an interesting question.
And I interrupted there. Can you reiterate what you were saying about SolidWorks Motion really quick?
Yeah. So SolidWorks Motion is part of SolidWorks Premium. There are some motion characteristics and tools that you can do in SolidWorks Standard and SolidWorks Professional, but the real analysis side of it, it requires SolidWorks Premium to do what I'm going to show you guys today. So I have SolidWorks Motion turned on, and you'll notice there's a motion study. There's always a motion study defined at the bottom of every single part and every single assembly. So by clicking that and opening it, you'll notice a little pull-down menu here where I have the option to create an animation, a basic motion, or a motion analysis. Okay, so what's the difference? Honestly, sometimes
what is the difference?
What is the difference? I sometimes forget myself. So this is an opportunity for me to talk about what I think really is the SolidWorks help is actually really helpful. And I urge you guys to use it. So little question mark and hit the help button here. All I know is last time. So if I type in some words that I know that animation is a word that I know, and I know that basic motion is a word that I know that has to do with this question that I want to answer, and hit enter, and I come up with 31 results. And because I've done this before, I know that the second result, but I mean, the second result's not so bad. This tells me exactly the difference from an animation to basic motion to a motion analysis, right? So with animation, we can put motors, but we can't really back out any data, right? With basic motion, you still add motors. It takes into account like the mass of your parts, but again, you can't do things like inverse kinematics. Can't do that. When you want to get into real kinematics, things like backing out the torque of a motor or looking at real, like more quantitative information, you really have to run a motion analysis. But you can get pretty far with basic motion if you just want to see what's going on.
So basic motion will kind of allow you to drive something with a motor or something like that, but you want to specifically get the feedback and some more characteristics from the model, basically.
I do. Yeah, that's really what I want here. All right. So you may have noticed, Jeremy, and been confused. Why do I set these drums able to move up and down?
Yeah,
why don't you just stick them on the wheel and be good? Well, the reason for that is because when you create contact in a motion analysis, you want to like gently apply contact. If you have two parts that are currently touching, in all likelihood, they're probably interfering. And that makes motion doesn't like that. Really, rigid body dynamics as a tool doesn't like that. As an analysis tool doesn't like that. So let's start by talking about a game plan of what we're going to do here. So the first thing we do is we're going to take our two drums and we're going to move them up towards the wheels. At the same time, we're going to have the bike. We're going to turn gravity on and have the bike slowly fall onto the wheels, right? So create a really organic connection there. And after they're kind of touching and that contact is set up, then we're going to spin the drum and see the motion take place, right? So it's kind of a stepwise process. So the first thing I'm going to do Choose motion analysis, right? Because that's the one where I can get most information back. And I'm going to create a motor, but it's not really a motor. It's more of an actuator. So I'll choose this motor icon, and I want this to be a linear motor. And again, I'm going to get some use of these little cubes that I extracted here on the end of this axle, because these really help me with directions. So I'll choose this top face, and I want to move that a certain distance up. So again, I'm just going to try and guess here. So I want to move it a distance. I want to say this can be, say, 6 inches. And I want that to start at 0 seconds, and I want it to complete moving up after 1 second. I can even click this little plot. This is pretty slick, right? This is going to give me a visual, kind of visual feedback saying, okay, in -7 seconds, -1 second. So here's my 0 second line. So at 0 seconds, it's going to start moving up, and it's get 6 inches. You can see here, and then at 1 second, it's just going to stay at 6 inches. That's perfect. That's what I want it to do. All right. So I'm just going to quickly run the analysis. Why not? Let's see what happens. What did it do? So the first time you hit the run button, it takes a few seconds to think, but something like this will solve pretty darn quickly, right? Okay, there we go. That's it. That's all I wanted it to do. Perfect. I just want it to move up, and that's exactly what it's doing. Drums here, drums moving 6 inches, done. So the next thing I want to do is I want the drums to rotate. So I've calculated based on the circumference of these drums that 75 RPM is equal to about 14 miles an hour, which if you're bombing a hill that has 2-inch bumps, you're going at a pretty good clip, right? But a mountain bike should be able to handle that and much, much, much more. Okay, so let's set that as well. Okay, so on a rotary motor, okay, remember I only have to connect or have to turn one of these drums because they're mated together with that gear mate. I only have to choose one, and they will both rotate in sync. All right, and we'll choose 75 RPM. And I want that to just run at a constant speed. It's fine. I don't want that to change or do anything. But I don't want it to start until after I've moved the drums up and the wheels have connected. So if you look here, so on this bottom timeline, if you've ever used an animation software in the past, you'll kind of recognize this, right? 0, 1, 2, 3, 4, 5, 6 seconds. This is kind of like the simulated time. And we're setting events to happen at, say, different intervals. So this rotary motor, I want this to turn on at 1 second. I want it to turn on here. And now it's set. See this little diamond shape here? This is called the keyframe. So what I can do is I can just move this keyframe, push it over to 1 second, and then that'll start that motor at 1 second. It's super easy and extremely visual.
So if you've ever used the animation capabilities of the motion, it works the exact same way, basically.
Yep, exact same way. So now I have that starting at 1 second. And now that we're here, let's go ahead and kind of give a little preview, see what we did and see if it worked. Okay, it's moving up 6 inches, and now they're rotating. Cool. All right. So that's working pretty well. So the next thing we have to do is now it's time to apply contact. And that is pretty simple, right? And it does some pretty cool things. So I have my little contact button here, and I want to create contact between this tire and this drum. Makes sense, right? What's pretty neat are some of these kind of like pre-cooked like material configurations, right? So I'm going to say that, my first selection is dry rubber. It's tire. And my drum, we'll call that dry steel. And by doing that, it's going to set the friction, the static friction, and the kinematic friction, as well as some like elastic properties like restitution coefficient, all that important stuff that really defines what happens when these two bodies come into contact.
And this is where, when we do a motion analysis, we're going well beyond creating basic mates between these components. And you're actually defining how the two materials will actually touch and interact with each other and engage with each other as you're going through this.
That's totally right. Yeah, this is really where the motion analysis, as opposed, like you're saying, as opposed to the basic motion or animation, is we're really using the horsepower of this pretty intense solver that's running in the background when we run this analysis. All right, so I'm not going to run this one live because it does take a little while. This one takes about a minute to run. So I have kind of a set of results that I've ran before, and this is just with contact and rotation. So remember, all I've done at this point is I've used my linear motor, right, to move the drums up. I've created my rotary motor that I've delayed by about a second. This is just less than a second. And I've defined my two solid bodies and gravity. Oh yeah, I forgot to apply gravity here. So I'm back to the analysis we're working on. I'm just going to turn gravity on. And we can see I want to be in the Y direction. So if we look down here in the bottom right corner, we get this nice little call out, right? We get this green arrow that says gravity that way. And I'm like, yes, that's the way, that's the direction I want gravity. So I'll turn that on. Okay, so back to my result file, right? I'm kind of switching back and forth. This is a different file where I've already ran this one. So what do you think is going to happen if when we hit play here, Jeremy?
So you have gravity set. So you made the drums come up and start spinning. So these drums are going to come up and engage and start spinning, and the bike's going to fall on it. Will those contacts you created actually start spinning the wheels of the bike?
That I sincerely hope so. Let's check it out.
Okay.
Okay. So drums come up, start spinning, and cool.
Oh, it's doing a little pop a wheelie there on the front.
That's a little pop a wheelie here. Yeah. It's popping a little wheelie. And we notice that our shocks are totally compressed. And the reason for that is because we haven't defined anything happening there. There's no spring. So it just basically once it makes contact with the drum, the shocks just totally fully compress. And just to let you know, this is at 0.25 speed. At full speed, you'll see this thing's moving pretty quick, right? So it's about 15 miles an hour. It's like bump, 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 bump. Pretty rough ride.
So are these shocks compressing because we need to like tell it like it's got a spring or a dampener in it or something like that? Like
that's exactly where we're going. So we're just kind of doing a stepwise solution. We're making sure one thing works before we move on to the next, kind of the scientific method in some ways. We want to make sure, okay, this works. Now let's start adding complexity once we know the other stuff is working.
Got a couple comments just came in. Once you hit play, I think people's eyes kind of went, wow, okay, that Taurus IED says that's really cool. Wikichedia says, perfect. I've been working on a design for a while. This is just what I needed to kick me into gear. So,
dude,
yeah,
nice.
Awesome.
That's awesome. That's awesome.
Sometimes it's like you're putting the ingredients in and you're waiting to see that product come out. And I think as soon as you hit play, people went, oh, I totally get it. Like how the simulation is going to work now. So,
yep. And it looks kind of real. And like one of the rules of like rigid body dynamics that I've always thought, like using the motion tool, if it looks realistic, it probably is. If it looks unrealistic, it probably is not realistic. So just use that kind of take the temperature on how realistic it looks. All right. So the next thing we're gonna do is add some springs. So I'll add a spring to my rear shock here. So before I do that, I'm going to change the transparency. I'm going to go ahead and right click and select change transparency. And this is going to help me give me access to some of the faces that I need for adding the spring. So I'll add a spring, and you see it's pretty simple. Go ahead and choose this face, select other. I'll choose this face. Didn't want to select it. What about, maybe I'll choose this one first. Let's see if it selects it now. Choose select other. There. And we get a cute little icon of a spring. Isn't that cool? So it gives me the visual feedback to say, okay, so there's a spring here. Now in real life, right? Remember I mentioned earlier, this is a gas spring in a real bike, but we can estimate that and simulate how a gas spring behaves if we want. Again, I'm going to keep this pretty simple here, but we can choose this kx to the e formulation to choose a progressive spring, and you can really, really dial in this behavior really, really realistically. But I'm going to keep it at linear.
So can you define whether or not this spring works in compression or contraction?
I think so. I think it really works only. I think it works both ways. I don't think you can define one way or the other the way you can do in like FEA. Yeah, I think it's one way or the other. Okay, so I'm just going to set a value for our pounds feet per inch. Again, you can find a lot of documentation on the internet that's going to associate the PSI of your cylinder to the spring rate. So I'm just kind of throwing this is just kind of a dart that I've thrown based on my bike and my weight and all of those things. Okay, so we add a spring here. All right, we do the same in the front. So I'm going to make this transparent and add a spring here. Okay, spring on this edge. Nope, not that edge, right on this face. Perfect. And again, maybe hopefully select other. It behaves a little better for me right now. Perfect. All right, so I have a little spring there. And I'm going to give this a much lower spring rate, which is true of all mountain bikes. The spring rate in the rear shock is sometimes an order of magnitude or more stiff than the front shock because most of your weight is at the rear of the bike. Okay, yeah, and down here we can change the display. So if I don't like that, if I want the spring to be, say, a little bigger or a number of turns, right? This is all just visual stuff. So that's kind of fun. So I'm going to add another spring on this other side. And this is more of a test for the chat. And I'm doing this just for fun. But why, does anyone know in the chat why you probably wouldn't do this in real life? Why would you not put a spring on both sides? And I'll give people a second to see if anyone can answer that. And if anybody is really understands, has ever looked into one of these, a shock on a mountain bike. So I'll give everybody a second.
Watch the chat there, see if anybody comes in. Why would we normally not put a spring on either side?
On both sides.
On both sides of that shock.
Why wouldn't you put it on both sides?
And they're a little bit delayed, Andrew. So we got to give them a quick a second here to see if they'll answer.
I'll give everybody a few seconds. All right, so we have our 3 springs. 1, 2, 3 springs. Now, what we haven't added yet is the rider weight and the mass of all the parts that we took off the bike, right? And so we can now add something, just a simple force. Okay, now I'm gonna say all of the weight of the rider and all the extra parts that I've taken off, my water bottle, my shoes, my helmet, everything. I'm going to add that to, this is called the bottom bracket of the bike. And this is where the crankshaft and the pedals connect to this hole. So usually when you're bombing a hill, when you're going down a hill, you're usually out of the saddle. So like 90% of your weight is on your pedals and a very small amount of your weight is on your front handlebars. So I'm going to add all the weight here, and this is going to simulate the rider. So
we are getting a ton of responses to your question. I'll let you finish this, and then we're going to go through those questions. Okay.
Love it. Oh,
we're going to go. There's a lot. Like I think there's like 15 different.
I like it. All right, I'm psyched that people are stoked about that. All right, so I'm going to change the direction of the weight. And for me, so I'm just going to add a constant weight. I'm actually going to add a step function here, right? I'm going to add a step function here. And at 0 seconds, I want there to be no weight applied. Remember, the first second is when we're getting everything tuned up for the analysis itself. So I want to apply the weight slowly. So at 0 seconds, no mass. And at 1 second, I'm going to add 170 pounds, that's about my weight plus all the water bottles and all the stuff I've taken off the bike. Comes out to about 170.
And is this also taking into consideration the weight of the components? So yes. Like the frame. Okay. So
yep. Well, no, not the weight of the weight of the components. That's baked into the part itself.
That's what I meant. Yeah. Materials. So you don't have to think about any of that then.
Yeah. Right? Don't have to think about any of that. That's a great point, Jeremy, that I missed. Is that that I've applied the accurate materials to all these parts. So the weight of them, their mass is pretty right on. All right. So now I've added my springs and I've added the rider weight. So I'm going to just flip back.
Okay. Well, you flip back. Let's go to the questions. Yeah, let's go to this question because we got a lot.
Okay. Can't wait.
I'm going to go through these randomly because you told me about this ahead of time. I know the answer. So, okay. I'm trying to find the ones that it maybe is not. Is it because your weight is more on the rear wheel?
Weight is more on the rear wheel. No, but that is but that is true. Most of the weight, like you do push yourself back on the bike when you're going down a hill, and you do put more weight on the rear wheel. But that's not why you wouldn't put a spring on both sides of the fork.
All right. Uh, is it because I'm not sure. This one says one is an observer question mark.
One is an observer.
Like,
I
is it
wonder if
just
what they mean
is
is
it
that
just is it like a cost cutting where they like only build the spring into one side?
it's not a cost cutting. It's actually very functional. The reason why
Okay.
you really only have a spring on one side. But that's a good question. And maybe as an observer, maybe they also meant like if you wanted to back out kind of reaction forces on both sides.
Okay. All right. So we're gonna go to it. There were a lot of people who got it right. Is it because the
Nice.
other side contains a dampener?
Boom. That's correct. Right. You
All
take these
right.
things apart. One side has a spring and the other side has a damper. And that's kind of the next phase of where we're going is damping. That is like probably one of the most critical parts of designing a suspension for a mountain bike and designing a good suspension system. Okay, so now we have contact, rotation, springs, gravity, and rider weight. Let's see what this one looks like. Okay, all right. This is starting to look somewhat realistic,
Look at that.
but
Your shocks are working. You're not popping wheelies anymore.
not popping wheelies. But what do you think about that ride? What if you were sitting on this thing? How would that feel, Jeremy?
I would ask to have the seat or saddle put back on it. I'm not gonna lie.
Yeah, that probably would help. That help. But I mean, it's jiggling all over the
Yeah,
place,
I
right?
don't know if I could keep that thing straight if I wanted to.
Yeah, you probably couldn't because a spring is great. A spring takes a lot of the force of like a bump and it uses that energy to compress a spring. But you really need a damper to improve ride quality and comfort and also keep the rubber side on the dirt. That's the most
Right.
important part. All right, cool. So we're getting somewhere. So let's go back to our other study. And now we're going to go back into these springs and we're going to edit these springs a little bit. So you notice that there's a little choice for a damper here. So on the rear shock, again, this is all something that you can find on the literature for, say, Fox Racing or rock shocks or any of the shocks that you use. You can find information like what is the damping rate. And the damping rate is also something that every mountain bike shock will have an adjustment for, and they call it spring back. And you can set how much you want, how much damping you want. You can either turn it off, which is insane, or you can roll it on and really set it to your weight so you're really maximized for, again, which hill you're going down and what size kind of bumps you're going to be hitting. Okay, so I'm going to set the rear shock damping rate at 3 pounds per inch per second. And the front damper, I'm just going to add it to each of them. I'll turn that damper on. And this one, I'll say 0.5. And again, this next spring, we'll also set this at 0.5. So this, when you add things like damping and contact and springs, this all kind of extends the solve time. So this one takes about 10 minutes to run.
Okay.
So let's see how this looks. So this is the analysis that what I would consider is called critically damped. And critically damped, that's kind of the goal of the whole thing, is where you want your shocks to take some, like if you look, let's zoom in on the front shock. You see that it's taking on the impact of hitting the bump, right, by the shock compressing, but it's immediately pushing the wheel back down onto the riding surface. So you're maximizing that force on the dirt, which gives you grip and which makes the riding more comfortable. So if we look here, we're kind of jiggling a little bit, but you see this is where the handlebars connect.
Sure.
And so we want to try and isolate all of the movement in the shock, and so it doesn't translate into the handlebar. Again, that is the goal of the whole thing there, and also, of course, the saddle. We want to keep this as motion free as possible. So let's take a look at a couple other studies here. So that is called critically damped. That's really what we're going for. But let's look at
That's like the Goldilocks zone or whatever they would
that's
say, right?
it's the Goldilocks zone, exactly. So let's look at what an overdamped system looks like. That means the damper is cranked up way too high. Now, every mountain bike also has this setting too, where it's basically called a lockout. You basically tell your shocks to not do anything, not to spring at all, to act totally rigid. This is great for climbing, because when you're climbing, you want to make sure that all the energy and all the power you're putting into the pedals goes into turning the rear wheel instead of compressing the shocks all over the place. So this is what it looks like when you're overdamped, right? This just looks like bump, bump. If I set this at normal speed, you'll see this is pretty impact-ridden ride. It's not moving so much, but those jolts are pretty serious.
So this would be more like the mountain bike I had when I was a kid.
Yeah, probably. Or a fully rigid mountain bike, or trying to.
Well, that's what I mean. That's what I had, when I was a
yeah.
kid. Like that was before suspension was like a thing.
Yep. And here we're going back to our underdamped system where we have no damper at all. So I took a few minutes and.
So can you compare these? Like, is there a way to I mean, this is cool that you can show these, but like numerically, can we look at these and see how different they are from one another?
Absolutely. And that's exactly where I was going. That's awesome, Jeremy.
Okay.
Okay. So I can create what's called an XY plot. And I'm going to select my category. I want to look at displacement. And I want to look at linear displacement. And I want to just understand in the Y direction. That's the up and down direction. And I want to see kind of what sort of effect this has on my handlebars, right? So we're just going to look at this, at the ring at the very top of this called the head tube of the neck. And this is everything that's translated into this zone is going to be translated right into my hands, right when I'm riding. And I can get this really rad plot. So if I zoom out here, it'll even kind of show me where I'm at in the plot when I hit play. And we can see this is the kind of the jagged motion. So the last thing I wanted to show today is I pulled this plot from all of them and put them into this like a little PowerPoint presentation. Okay, so here we have an underdamped suspension, and we can see lots of movement. This is the distance, and this is with respect to time. So lots of movement when we have no damper at all. Now, when we have overdamped, we have less movement. But can you see this really sharp angle from a flat to go?
Sure.
So that translates to like a big impact, right?
I'm going to need a really well padded saddle if I
really well padded saddle. Yeah. Like if you remember, like like early calculus, right? You take your distance and you take the derivative of that, and you get velocity. You take the derivative of that, you get acceleration. You take the derivative of that, and you get this factor called jerk, right? And that's like the fourth derivative of position. And this would have a tremendous amount of jerk at this point. It'd be like a big peak, right? Because you're going from, it's almost like a sharp angle. We want to stay away from sharp angles. So now when we go to critically damped, we can see that overall the waveform is shrunk, but also we see these nice round transitions as we're going from one bump to the next. And this really is the goal of the whole thing. And it makes it a little easier to see if you overlay all of them, right? The critically damped scenario is not only the smallest amount of displacement, but the smoothest displacement of all of them. Yeah.
So really cool, Andrew. You've shown not only how to set up this virtual fixture, but also how using SolidWorks Motion, you were able to pull all this information out of it so you could literally compare it like side by side as you look at this. I think it's super valuable. We've talked about a lot of, I think when we say the word simulation, people think meshing and they think stress. The reality is motion plays a critical part in that whole process as well.
Absolutely. And you can test a lot of really cool things virtually before you even, and like something like this, it's fun to do, but I could also really use this. If I knew some information about a ride I was going on, I probably wouldn't do this too often, I'll be totally honest. But once you set it up once, I can just like play with the spring rate and damping, and I can kind of determine based on the terrain and the speed I want to go, what is my most optimum setup of my front and rear suspension. Then I can just basically use my little pump and pump it up to that level and dial in my my damping for each, and I could get a pretty good tuned system. Now, professional mountain bikers, they definitely do this. They have a whole team that does this. And so that's pretty slick.
So
Yeah.
Mike Sandy made a comment that if you want a good engineering insult, it would be you're the fourth derivative of position. I like that. I'll have
Nice.
to that.
Yeah, you're the fourth derivative position. That'd be like one of those like shirts that always come up on the right side of a web page that
Yeah.
Yeah.
Yeah, when I was a kid, Pluto was still a planet. Or back in my day, I want that shirt.
Big ups, Pluto.
Yeah.
Man.
Well, Andrew, I want to thank you. I want to thank everybody in the chat for joining us here today. Hopefully everybody enjoyed seeing how you can virtually test your SolidWorks models right inside of SolidWorks. I thought this was extremely informative. And go back and watch it again at the beginning when Andrew was setting it up. He covered a ton of tips and tricks. I loved component preview for mating. He did the temporary fixed and group components quite a bit as he went through there. Good look at how limit makes works, copy with mates, and some cool tips with breadcrumbs as well on top of all this other great content we saw. Next week, if you want to tune in and join us here again on YouTube, we are going to have Exploring 3D Experience Works. They're going to be talking about CAD files and beyond. So I think that'd be a great one to tune into, looking beyond your CAD data and what you can do with it. In 2 weeks, we're going to be back here for live design. And then we'll have SolidWorks live on August 5th. I want to thank everybody for tuning in. And again, if you don't want to miss one of our live broadcasts, make sure you subscribe to our YouTube channel. And if you hit the bell notification icon, you'll get notified whenever we go live. Until next week, we'll see you later.